Gravity is one of the most popular forces in our daily life, yet it remains one of the most mysterious forces in the universe. Every time an apple falls from a tree, every time the moon circles our planet, and every time galaxies spin through cosmic space, gravity is quietly shaping these motions. For centuries, humans have tried to understand why objects fall and why celestial bodies move through the sky. Early civilizations imagined invisible forces or divine influences controlling the heavens. Later, scientists began searching for deeper explanations. From Isaac Newton's groundbreaking discoveries in the 17th century to Albert Einstein's revolutionary ideas about space-time in the 20th century, gravity has remained one of the most fascinating puzzles in science. Yet, even today, gravity still holds secrets. Scientists continue to explore how it works at the largest cosmic scales and the smallest quantum levels. The more we learn about gravity, the more we realize that this invisible force connects everything in the universe. Gravity exists everywhere. Gravity exists in every object with mass creates a gravitational pull. Even the smallest particles exert a tiny gravitational influence on their surroundings. When objects become large, such as planets or stars, their gravitational effects become powerful enough to influence other objects across great distances. Without gravity, the universe would look entirely different. There would be no stars forming from clouds of gas, no planets orbiting those stars, and no galaxies gathering into massive cosmic structures. Some scientists debate whether gravity behaves differently across enormous cosmic distances. Observations of galaxy motion suggest that unseen matter, known as dark matter, may influence gravity's effects. While this debate continues, one insight remains clear: gravity connects everything in the universe through invisible relationships. Gravity is not just a force. For centuries, scientists have believed gravity was simply a force pulling objects towards one another. Isaac Newton famously described gravity as an attractive force between masses. His theory explained planetary motion with remarkable accuracy and remained the foundation of physics for hundreds of years. But in the early 20th century, Albert Einstein proposed something even more extraordinary. According to Einstein's general theory of relativity, gravity is not just a force. Instead, gravity emerges from the way mass bends the fabric of space and time. Massive objects such as planets and stars curve space-time around them. Other objects move along these curves, creating what we perceive as gravitational attraction. Some physicists still debate whether gravity should ultimately be described as a geometric effect or as a fundamental particle interaction. But Einstein's insight transformed modern physics and reshaped how we understand the structure of the universe. Gravity controls planetary motion. Gravity is responsible for one of the most elegant phenomena in the universe, that is planetary motion. The sun's immense gravitational pull holds the planets in orbit, creating a delicate balance between motion and attraction. Without gravity, planets would not circle stars. They would simply drift through space in straight lines. Gravity creates what scientists sometimes call the cosmic dance of celestial bodies. Planets orbit stars, moons orbit planets, and galaxies rotate through the universe. Some astronomers study planetary systems around distant stars to understand how gravity shapes these complex arrangements. The existence of stable planetary orbits is also essential for life. Without gravity, maintaining Earth's orbit at the right distance from the Sun, our planet might not support the conditions needed for life. Gravity affects time. Animation of clocks ticking slower near a massive object. Satellite orbiting Earth. One of the most surprising discoveries in modern physics is that gravity can influence time itself. According to Einstein's theory, time passes more slowly in regions where gravity is stronger. This effect is called as gravitational time dilation. Although the effect is extremely small on the Earth, it becomes significant near massive objects like neutron stars or black holes. Scientists have confirmed this phenomenon using precise atomic clocks placed at different altitudes. Even GPS satellites must account for gravitational time dilation to maintain accurate navigation systems. What once seemed like a science fiction that time itself could change depending on gravity is now a well tested part of modern physics. Gravity creates black holes. Black holes represent one of the most extreme consequences of gravity. When massive stars exhaust their nuclear fuel, they collapse under their own gravitational force. In some cases, the collapse becomes so intense that the star's mass compresses into an incredibly small region. The gravitational pull becomes so strong that nothing, not even light, can escape. For many years, black holes were considered purely theoretical. Some scientists even doubted their existence. However, modern observations, including the first image of a black hole, have confirmed that these extraordinary objects are real. Black holes offer scientists a unique laboratory for studying gravity under the most extreme conditions imaginable. Gravity played a fundamental role in shaping the universe after the Big Bang. In the early universe, matter existed as scattered particles. Over time, gravitational attraction pulled these particles together into clouds of gas. These clouds eventually formed stars and galaxies. Gravity continues to influence galaxies today, guiding their rotations and interactions. However, astronomers discovered something puzzling. Galaxies appear to rotate faster than gravity alone can explain. This mystery has led scientists to propose the existence of dark matter, an invisible substance that may influence gravitational behavior. While dark matter has not yet been directly observed, its gravitational effects may help explaining the structure of the universe. Gravitational waves. In 2015, scientists made an extraordinary discovery. They detected gravitational waves, ripples in the fabric of space-time, created by massive cosmic events. When black holes collided, they released enormous amounts of energy in the form of gravitational waves. Detecting these waves required incredibly sensitive instruments capable of measuring distortions smaller than a proton. The discovery confirmed a prediction Einstein made nearly a century earlier. Gravitational waves opened a completely new way of observing the universe. Scientists can now listen to cosmic events that were previously invisible. Gravity is the weakest force. Surprisingly, gravity is actually the weakest of the four fundamental forces of nature. Electromagnetic forces and nuclear forces are far stronger at small scales. Yet, gravity dominates the universe on a large scales. This happens because gravity always attracts, unlike electromagnetic forces, which can cancel each other out. Gravity accumulates. Even though it is weak at the particle level, gravity becomes the dominant force shaping stars, planets, and galaxies. Despite centuries of study, gravity remains one of physics' greatest mysteries. Scientists are still searching for a theory that fully combines gravity with quantum mechanics. Some theories suggest that extra spatial dimensions, others propose undiscovered particles known as gravitons. The search for a deeper understanding of gravity continues to drive scientific exploration. Gravity shapes everything from falling objects to the motion of galaxies. From Newton's discoveries to Einstein's revolutionary insights, gravity has inspired some of humanity's greatest scientific breakthroughs. Yet many questions remains unanswered. Sometimes the most ordinary forces hide the most extraordinary secrets. and gravity continues to remind us that the universe still holds mysteries waiting to be discovered. Thank you. Have a nice